This is the RIW 8000, a radial axial ring rolling machine built by SMS Mir, one of Germany's most respected names in heavy industrial machinery. And if the word ring rolling sounds simple, trust me, what this machine does is anything but. So let's talk about what's actually happening here. Ring rolling is a hot forming process, meaning the metal is heated to extreme temperatures before it's shaped. In the case of the RIW 8000, we're talking about rings that can weigh up to 8,000 kilograms and reach diameters of several meters. These aren't decorative rings, they're industrial components destined for wind turbines, aerospace engines, oil rigs, and heavy equipment. The process begins with a solid billet of steel. This billet is first heated in a furnace to temperatures typically between 1,100 and 1,250 degrees Celsius, hot enough to glow a deep, vivid orange. At that temperature, steel becomes plastic, not liquid, but workable, like clay in the hands of a sculptor. From there, the billet is pressed on a vertical forging press. A powerful punch drives straight down through the center of the heated billet, creating what's called a preform, essentially a thick, donut-shaped disc of hot metal. This step alone requires thousands of tons of force. Now here's where it gets fascinating. That preform is placed onto the RIW 8000's main roll, a massive, motorized cylinder, and the machine goes to work. The main roll rotates against the inside of the ring, while a second roll, called the idle roll, presses from the outside. Together, they squeeze the metal thinner and thinner while the ring grows larger in diameter. All of this is happening while the metal is still glowing. But what makes the RIW 8000 exceptional is the radial axial design. Most older ring rollers only compress the ring from the sides. This machine works from two directions simultaneously: radially, growing the ring wider, and axially, controlling the height with two conical rolls pressing from above and below. The result is a ring that's geometrically precise without the need for excessive machining afterward. The machine's control system is fully automated, using sensors and computer feedback to maintain consistent wall thickness and dimensional tolerances throughout the rolling cycle. When the rolling is complete, the ring is removed and slowly cooled under controlled conditions to relieve internal stress. Then it heads to machining, lathes, mills, and grinders to achieve the final precise dimensions required. What you're watching is the production of Böhler stainless steel, carried out by the Oristar Group. Now, Böhler is a name that carries serious weight in the materials world. What Oristar produces, using the Böhler brand, are high-grade stainless and tool steels, chromium, nickel, molybdenum blends that resist corrosion, hold extreme hardness, and perform reliably under punishing conditions. The production process begins in the electric arc furnace, or EAF. Scrap steel and carefully measured alloy additions are melted together at temperatures exceeding 1,600 degrees Celsius. It's loud, it's bright, and it's breathtaking, raw energy transforming scrap into something refined. Once the molten steel reaches the right chemical composition, it moves to the ladle furnace for secondary metallurgy, fine-tuning the temperature and chemistry before casting. From there, the steel is cast into billets or slabs using continuous casting, a process where liquid metal is poured into a mold and drawn out as a solid strand. This is a far cry from the ingot pouring methods used decades ago, and the quality improvement is dramatic. Those billets then go through hot rolling mills, massive machines that compress and elongate the steel at high temperature into flat bars, round bars, or sheets depending on the end use. Each pass through the rolls refines the internal grain structure of the steel, improving its mechanical properties. What makes Böhler-grade material special is the strict quality control throughout. Chemistry is tested at every stage. Samples are pulled and analyzed. Hardness is measured. Surface defects are tracked and addressed. This is Friuli Forge SRL, an Italian forging powerhouse located in the Friuli region of northeastern Italy, a place with deep industrial roots. And the star of the show? A 500-ton hydraulic forging press. That's 5 million pounds of force, focused into a controlled, repeatable stroke that shapes red-hot billets of steel into precision near-net-shaped components. The process begins with raw steel stock, heated in a gas furnace to temperatures between 100 and 250 degrees Celsius, glowing orange, almost alive. The billet is placed into a precisely machined die set, and with one controlled press stroke, the metal flows into the die cavity, filling every contour. Flash, the excess material squeezed out at the parting line, is later trimmed away. What makes forged parts special isn't just their shape, it's their internal grain structure. The forging process aligns the steel's crystalline grain flow with the part's geometry, resulting in components that are dramatically stronger, tougher, and more fatigue-resistant than anything machined from solid bar stock. Now, if you've ever wondered what goes into building the pipelines that carry oil, gas, and water across continents, this one's going to blow your mind. We're inside the ArcelorMittal Jubail plant in Saudi Arabia, one of the most advanced steel pipe manufacturing facilities on the planet. And what they make here isn't just any pipe, it's seamless steel pipe. No welds, no joints, no weak points. Just one solid, continuous piece of steel from end to end. Here's how it works. It all starts with a solid steel billet, a thick, heavy cylinder of raw steel heated inside a rotary hearth furnace to around 200 degrees Fahrenheit. At that temperature, steel becomes almost like clay, ready to be shaped. That glowing billet then gets pushed through what's called a piercing mill. Two barrel-shaped rolls grip the steel from opposite sides and rotate it at high speed. Right at the center, a pointed mandrel, a hardened steel rod, drives straight through the billet, punching a perfect hole down the middle. That's your tube, born right there. From there, the hollow shell travels through a continuous rolling mill, a series of precision roll stands that gradually stretch and shape the pipe to exact dimensions. Each pass refines the wall thickness, roundness, and diameter with incredible accuracy. Finally, the pipe goes through a sizing and straightening process, then gets heat-treated for strength, ultrasonically tested for any hidden flaws, and inspected end-to-end before it ever leaves the facility. What you're watching is steel engineering at its finest, built tough enough to handle the demands of the world's most critical infrastructure.
Welcome to Parsan Makina Parçaları Sanayi AŞ, one of Turkey's premier forging manufacturers, producing automotive components that meet global standards for some of the most demanding vehicle applications on the market. Let's start with the leaf springs. These are the long, slightly curved strips of steel that act as suspension components, primarily in trucks and commercial vehicles. Their job is deceptively simple: flex under load and spring back. But doing that reliably for hundreds of thousands of miles requires steel with exceptional fatigue strength and precise geometry. At Parsan, the process starts with high-carbon spring steel bars, typically grades like 51 CrV4 or 55 CR3, known for their ability to absorb and release energy without permanent deformation. The bars are heated in induction or gas furnaces to forging temperature, around 1050 to 1150 degrees Celsius. Then they're fed into hot stamping presses, which form the cambered arc shape of the spring leaf in one or two powerful strokes. After forming, each leaf goes through a closely monitored heat treatment cycle, quenching in oil or polymer, then tempering, to develop the precise hardness and toughness required. Too hard and it'll crack, too soft and it'll sag. Getting that balance right is what separates average springs from ones that last. Now for the gears, and this is where forging really shines. Automotive gears are among the most highly stressed components in any vehicle. They transmit torque, change direction of force, and operate at high speeds with very little room for error. Parson forges gear blanks using closed-die drop forging, a process where heated steel billets are struck between matched upper and lower dies with extreme force, filling the die cavity to produce near-net-shaped forgings. The dies themselves are precision machined to match the final gear geometry closely, so material is used efficiently and grain flow follows the shape of the part, which dramatically improves strength compared to machined from bar alternatives. After forming, the gear blanks go through machining, hobbing, shaping, or grinding to cut the final tooth profile to micron-level accuracy. Then heat treatment and surface finishing bring the component to final specification.